All right, so we're starting in Chapter 9, talking about sequences and series. Today we're just going to talk about sequences. This unit is pretty short. We're essentially going to finish before spring break. We'll come back after spring break and do kind of some review. So our quiz is going to be after spring break, and then we do just one little thing between the quiz and the test. So we're going to finish this one. We're going to finish this unit pretty quickly.
So we don't have like a quiz or test next week?
We do not have a quiz or test next week. So a sequence. Sequence is what we're going to talk about today. A sequence is just a function. It's a special kind of function. It's just a function whose domain is the positive integers. And just as a reminder, positive integers, we mean 1, 2, 3, etc. So that makes our function a little easier in some ways than functions that we've worked with in the past. If we can have a finite sequence, we can have an infinite sequence. If we just keep, if our domain, if we can plug in any positive integer, we have an infinite sequence. If we only plug in certain positive integers, then we have a finite sequence. And instead of writing f of n, we write the terms. We call each part of the sequence each number is a term, and we write a sub n, where n is our positive integers, 1, 2, 3, 4. And the entire sequence, to write the entire sequence, we write in brackets, or in braces, I'm sorry, a sub n. So this means the entire sequence. So if we have, say, our sequences for the positive integers 1 through 10, this would be the way we could indicate that we're talking about the entire sequence. One term, we just write a sub n. An example of a sequence is the Fibonacci sequence. I just want to write an example. Fibonacci sequence is just a famous one. And that's just Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, da, 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 da. And we get the Fibonacci sequence by adding the two previous numbers. So 1 and 2 is 3, 2 and 3 is 5, 5 and 3 is 8, 5 and 8 is 13. So this would be an example of a sequence. This is a sub 1, a sub 2, a sub 3, etc. So just each individual number in the sequence is written as a with a subscript. Now, part of what we're going to do in this section is we're just to work with sequences. We'll be given an equation for the term of the sequence, and we want to write out the sequence. So we'll look at a couple of examples of that, just to get familiar with the idea of a sequence. Often we're given an equation, and we want to write out what the sequence is. So if we want to write the first 4 terms. And our equation, our formula, a sub n equals 2n plus 5. So this is the definition for our terms of our sequence. Writing the first 4 terms just means plug in the numbers 1 through 4 and write down what those are. So a sub 1 equals 2 times 1 plus 5, which is 7. A sub 2 is just 2 times 2 plus 5, which is 9. A sub 3, 2 times 3 plus 5, which is 11. And a sub 4 is 2 times 4 plus 5, which is 13. So we just plug in our positive integers and evaluate it, and each term, then we just write down each term. If we want to, we'll call this one A. Let's do another one. Any questions on this? Pretty straightforward. If we have our formula B sub n is 3 to the n minus 1. And we want to write down the first 4 terms. We're just plugging in the numbers 1 through 4 into my function. So B sub 1 is just 3 to the 1 minus 1, which is 3 to the 0, which is just 1. B2 is 3 to the 2 minus 1, which is 3. B3 is 3 to the 3 minus 1, which is 9. And B sub 4 is 3 to the 4 minus 1, which is 27. So we're just plugging in the first four integers and evaluating our function. Questions on that? All right. Let's look at our third example, C. This one is going to be important, an important one to pay attention to. If C sub n equals minus 1 to the n divided by n squared plus 1. And we want to write down the first 4 terms of this sequence. Whenever you see a minus 1 to a power, your terms are going to alternate signs. Because if I plug in an odd number for n, negative 1 to an odd power is going to be negative. If I plug in an even power for n, negative 1 to an even power is going to be positive. So whenever I have a negative 1 to a power, it's going to alternate, my terms are going to alternate signs. So let's plug in 1 through 4 here. C sub 1 is minus 1 to the first power over 1 squared plus 1, which is minus 1/2. C sub 2 is minus 1 squared over 2 squared plus 1, which is 1/5. C sub 3. Oh, sorry, I thought you had a...
Just told me I left a book for me.
C sub 3 is minus 1 to the third over 3 squared plus 1, which is minus 1/10. And C sub 4 is minus 1 to the fourth over 4 squared plus 1, which is 1/17. Well, when you're writing the terms of your sequence, usually you don't want, you're not looking for decimals. You wouldn't want to put negative 0.5, negative whatever. You want to leave it as a fraction, because part of what we're going to be doing with sequences and series is figuring out some things based on the pattern that we can see here. And if you write it as a decimal, it's a lot harder to see the pattern. I guess you could put it in your calculator and then change it from decimal to a fraction. That would work. But part of what we want to be able to do is start being able to recognize what the pattern is that's going on with these sequences. So whenever we see a -1 to the n power, you know you're going to alternate signs. So let me write a little bit more about that, because that's going to be kind of important when we're talking about sequences and series. So -1 to the n, if we have this as part of our sequence, odd powers are negative and even powers are positive. If we're looking for a sequence, or we have a sequence where the even powers are positive, or I'm sorry, the odd powers are positive and the even powers are negative, we can get that by writing -1 to the n plus 1. So if we have -1 to the n plus 1, it switches these around. The even powers, the even n, would give us a negative, and odd n would give us a positive. So if we want to switch it around and we want the numbers associated with our even n's, we can write a -1 to the n plus 1, and that will switch it around. And it'll be important to recognize when we have alternating signs, whether we get it alternating, whether we're negative when n is odd or negative when n is even, and be able to use these two for those two different things. Yes?
Is that the same rule when it's n minus 1?
Yes. If it's n minus 1, it would be the same. Because if you have an odd power, you subtract 1, you always get an even. So questions on that? So a big part of what we're doing here at the beginning is just, 1, getting familiar with sequences, and 2, getting to where we can start recognizing some patterns that we see when we look at terms of a sequence. And these two things are part of one thing that we're going to need to recognize when we look at these patterns. All right, let's talk about factorial notation, because that's going to be very important in sequences and series. And I think you may have talked about factorial a little bit at some point in Algebra 1, maybe Algebra 2, I'm not 100% sure. But factorial that comes up a lot in sequences and series. The way we write it is n exclamation point. And this is the same as what n factorial means, is we start at 1, 2 times 3 times 4, all the way up to, we're multiplying all these together, it's n minus 1 times n. So we're just multiplying all the numbers from 1 through n together times each other. So a couple of examples. One, and we define, before I do the examples, we define 0 factorial. 0 factorial is defined to be 1. So 1 factorial is just 1. 2 factorial is 1 times 2, and that equals 2. 3 factorial is 1 times 2 times 3, or 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. 5 factorial is 1 times 2 times 3 times 4, and I think that comes out to 120 times 5. Sorry, I left out the 5. So we just multiply all the numbers together. And your calculator will do factorials. I think it's in the math. I think it's in the math menu to do factorials on your calculator. So this is what a factorial is. And factorial follows the same order of operations as the exponents. So if we're thinking of PEMDAS or order of operations, factorial is in the same order of operations as exponents. So it's one of the first things. One of the first things we do. Parentheses, exponents. Factorials go along with exponents. So an example of that would be the difference between 2 times n factorial. That equals 2 times n factorial. 2n factorial is all the numbers 1 times 2 times 3 times ... all the way up to n minus 2, 2n minus 1, up to 2n. So whenever we see a factorial, it takes the same, it's in the same position in our order of operations as exponents. We would do the factorial before we multiplied. Here, because it's in parentheses, we do the factorial to the whole thing. Yeah, Cedric. What's that? So this tells me that I start at 1, and I multiply all the numbers together until I get to 2n. 1 less than 2n is 2n minus 1. 2 less than 2n is 2n minus 2. So just like if we do 6 factorial, we do 1 times 2 times 3 times 4 times 5 times 6. 5 is 6 minus 1. 4 is 6 minus 2. So I'm just writing that because I don't know what n is. I write it in terms of the variable. So if I were doing, if we didn't know what, if we had x and we wanted to write x factorial, we don't know what x is. X factorial is just 1. We always start at 1. 1 times 2 times 3 times 4 ... We're going all the way up to x. So the numbers before x are x minus 2, x minus 1, all the way up to x. So if x were 10, this number would be 9, this number would be 8. So it just reminds us that we're getting all the numbers all the way up to x. Okay? And we'll do a couple of examples of this. All right, any other questions? So let's do some examples with factorial notation. If we want to write the first 4 terms again, and our sequence a sub n is n squared over n factorial. We want to write the first 4 terms of this sequence. So we're just going to plug in 1 through 4 for each of our terms. So a sub 1 is 1 squared over 1 factorial, which is just 1. A sub 2 is going to be 2 squared over 2 factorial, which is 4 over 1 times 2, which is just 2. A sub 3 is 3 squared over 3 factorial, which is 9 over 3 times 2 times 1. 9 divided by 3 is 3, so I just get 3 halves. And a sub 4 is 4 squared over 4 factorial, and 4 factorial is 1 times 2 times 3 times 4. So that's 4 squared is 16 over 1 times 2 times 3 times 4. 16 divided by 4 is 4, so I get 4 over 6, and we can divide that, each of those by 2, so I get 2/3. So the nice thing about, one of the nice things about working with factorials is that we often can do a lot of cancellation before we calculate. So when you're working with factorials, you want to write, you're usually going to want to write out your factorial to see if you can get some cancellation before you start simplifying. And we'll do a couple of examples of how that works here in just a second. Any questions on writing my terms of my sequences using factorial notation? Thanks. All right, let's do a couple more examples of simplifying. So here on these, we just want to evaluate. So we want to evaluate 10 factorial over 2 factorial times 8 factorial. So what I'm going to do here is write 10 factorial as 1 times 2 times 3 times, and once you start recognizing the pattern, you won't have to write all these out. I'm just going to write it out so we see this. So 1 times 2 times so I'm just writing all the detail out. Yes? No, you wouldn't have to. I just wanted to separate this because this is 2 factorial and this is 8 factorial. Now anybody see what I can do here? This whole thing cancels with all of this. So I just get 9 times 10 divided by 2, which is 9 times 5, which is 45. Now another way I can look at this, I could write 10 factorial. 10 factorial is just 8 factorial times 9 times 10 over 2 factorial times 8 factorial. Because 8 factorial is all the numbers from 1 to 8 multiplied together. And to get to 9 and 10, I just multiply 9 and 10 at the end, and those just cancel. And then we end up with the same thing here. So that's just 45. So if you write it all out, you will definitely see it. If you can start recognizing that 10 factorial is 8 factorial times 9 times 10, you end up with this nice cancellation with factorials when you have fractions. Here I divided 10 by 2 to get my 5. Same thing here. 2 factorial is just 2 times 1, and that divides the 10 to give me 5. Now let's look at an an example with just variables. N factorial over n plus 1 factorial. Now if I write this out, if I write out my terms just like I did here, this is 1 times 2 times 3 times dot 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 times n minus 1 times n. So it's all the numbers from 1 to n multiplied by each other. On the bottom, I have 1 times 2 times 3 times dot 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 times n times n plus 1. This is all the numbers from 1 to n plus 1. So what cancels here? Everything all the way up to n. This whole thing is going to cancel with all of this. This is all the numbers from 1 to n multiplied together. This is all the numbers from 1 to n and one more multiplied by each other. So all I end up with here is 1 over n plus 1. And I could write this just like we did up here. I could write this as n factorial over n factorial times n plus 1. This is all the numbers from 1 to n and multiplying one more number. And my n factorials cancel, and that's 1 over n plus 1. So when we have fractions with factorial notation, look for how you can cancel most of the terms. And if it helps you to write out all the terms like this, 1 times 2 times 3, da 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 da, all the way up to your number, if that helps you see it, that's fine to do it that way. Questions on that? All right, one last thing to talk about and then we're done. Recursive sequences. So for a recursive sequence, it's a little different than the sequences that we talked about before. For a recursive sequence, we're given a couple of terms, and then we're given a rule to find the other terms from the first terms. So rather than just be given a formula, we have to know a couple of terms to write down a recursive sequence. So we're given one or more terms, and then the formula uses previous terms to get new terms. So an example of a recursive sequence would be we're given a sub 1 equals 5 and a sub n equals 3 a sub n minus 1 plus 2. And this is for n greater than or equal to 2. So we're given a sub 1, and then our formula tells us how to find the next term from the previous term. So this tells me a sub 2 equals 3 times a sub 1 plus 2. And in this case, that's 3 times 5 plus 2, which is 17. And then a sub 3 is going to be 3 times the previous term, 17 plus 2, and that equals 53. And my fourth term is going to be 3 times 53 plus 2, which gives me 161. So for recursive sequence, the only thing that's different about a recursive sequence is I have to know some of the terms to start, and the formula will tell me how to find the new terms from the previous terms. Questions on that part? Now there's just a couple more examples that I want to do, kind of going backwards with sequences. So if we have a sequence, we want to figure out the rule. So I want to do a couple of examples of that. So if we're given a sequence and we want to find the rule, we have to look for a pattern. So our example, your problems for these say find the most apparent nth term. So what this question is asking us is figure out the rule. So if we have the numbers, we want to figure out the rule. So my example, first example is going to be my sequences, my terms are 0, 3, 8, 15, and we want to figure out the rule for this sequence of numbers. So we need to figure out how the numbers are related to our integers that we plug into our formula, 1, 2, 3, 4, 5. So we need to figure out a rule here. And there's no one way to do these kinds of problems. It's a little bit intuition, a little bit recognizing patterns. What I would do with this one is I would say 0. I looked at this one this way. 0 equals 1 minus 1. 3 equals 2 minus 1. 8 equals 9 minus 1. 15 equals 16 minus 1. And I know that somehow 0 has to be related to the number 1. 3 has to be related to the number 2. Any?
3 plus 2 minus, yeah, 2 minus 1 does not equal 3.
3 is, sorry, 4 minus 1. 3 is 4 minus 1. So we need to relate these to somehow to the numbers 1, 2, 3, and this comes, like I said, it takes a little pattern recognition. It takes a little bit. As you do it more, you'll get a little bit better at it. I said that this is 1 squared minus 1, 2 squared minus 1, 3 squared minus 1, 4 squared minus 1. So I just recognized that 1, 4, 9, and 16 were powers of 2, 1, 2, 3, and 4. So my nth term equals n squared minus 1. Now there could be other formulas that would work for these. They say most apparent because you could come up with other more complicated rules for this. The most apparent just means the easiest one to figure out, but there can be other answers. Let's look at one more example and then we'll be done. We want to find the most apparent nth term. 1/2, 1/6, 1/24, 1/120th, and we want to find the nth term. Anybody recognize these numbers? Yes, it's n factorial. So if we start at n equals 1, this is 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial. So if we start at n equals 1, this is the nth term is 1 over n plus 1 factorial. So if I plug in 1 here, I get 2. If I plug in 2 here, I get 3. 3, I get 4. So that would be my nth term here. So these can be a little tricky. Like I said, take some experience, take some practice, take some intuition. As you do a few of them, you'll start to see more patterns. You'll start to recognize more patterns. And that's part of what we're doing here, is trying to recognize some patterns. Questions? All right, homework. All right, there you go.